As we continue our journey through the world of vector geometry, the next thing we're learning about is distances. I want to remind you, we're still only 4 lessons in on this. This is still a very new topic to many of you. So remember to be kind with yourselves. Remember to be patient as we learn and build up the machinery that we need to work with vectors. By the end of this chapter, we're going to be working through some challenging and amazing problems. But for now, be patient with yourself and let's keep developing these skills. So before we get started, let's take a deep breath. And let's begin. So we'll begin with a bit of vocabulary. The vocabulary word we're picking up right now is magnitude. Okay? The magnitude of a vector, AB, is just the length of that vector. The notation that we're going to use for this looks a lot like absolute value. So if you want to talk about the magnitude of a vector AB, you write the vector AB with, absolute value bars around it. Now, I've effectively got a little formula for you here, right? The magnitude of a vector in 3 dimensions with components x, y, and z, the magnitude of that vector is just going to be the square root of x squared plus y squared plus z squared. So you're just squaring each of the components and then taking the square root of it. Now, that might look familiar to you, right? If I take the z part off of this, that actually looks a little bit like sort of the formula for the hypotenuse of a right triangle. And it makes sense. What's happening here, if we're sort of thinking about what's going on, I'm gonna try and draw this for us a little bit. If you imagine, I'm gonna draw a box here. Okay. Imagine that we have a vector here that's going from one corner of this box up to the other corner of the box. Right? And the components of this vector are A, B, and C. We could sort of think of this thing as being a right triangle that's sitting inside of this box, and the hypotenuse of this thing would be found by squaring A and B and C, and then taking the square root of that thing. So I don't want to go into a lot of depth on that right now because I don't want this video to be super long, but the idea is that the reason this thing resembles the Pythagorean theorem is that it's effectively the Pythagorean theorem in 3 dimensions. So to find the magnitude of a vector, all you need to do is square the components and then take the square root of it. Okay, so I want to do a little bit of an example here, but I also want to do a little bit of a review on things that we've learned before. So I'm starting sort of with this recall question, right? If you have 2 points, A and B, how can you find the vector that goes between them? This is something I tried to make a big deal of in one of the earlier videos. So we learned previously that you can always find the vector AB by starting with the endpoint and subtracting off the beginning point, expressed as position vectors. Right? So if you want AB, you just do the OB vector, negative 2, 2, 1, and then subtract the A vector, 4, 1, negative 3. And when I subtract those things, I wind up with, let's see, negative 6, 1, and 4. So now as a follow-up to that, how could we find the distance between the points A and B? Well, we could do that by just finding the magnitude of AB. The magnitude of AB would be the square root of negative 6 squared plus 1 squared plus 4 squared. That'd be the square root of 36 plus 1 plus 16, which is the square root of 53. Now, I want to throw out there briefly, some of you may be aware or remember the distance formula between 2 points. You may remember that the distance formula was the square root of like x2 minus x1 squared, the difference in the x coordinates, plus y2 minus y1 squared, and then you square root the whole thing. Well, I mean, the distance formula in 3 dimensions also works. You just do it with a z2 minus z1. You subtract those components and square it. You could do the same thing here. You would have the square root of the difference of the x components, that would be 4 minus negative 2, squared, plus the difference in the y components, 1 minus 2 squared, and then the difference in the z components, so negative 3 minus 1 squared. Okay. So if I did that, I'd wind up with a square root of 6 squared plus negative 1 squared plus negative 4 squared, and hopefully you're catching on to what's happening here. It's the same numbers. I mean, the only difference here is that these ones seem to be negative and these ones were positive, but when these things get squared and square rooted, all of that difference goes away and we get the same thing. So I sort of want to point out that this concept of finding the magnitude of a vector and using the traditional distance formula really get us to the same result. So that may make you wonder, why do we need this new vocabulary? Why do I need this new complicated process? Ultimately, the distance formula and magnitudes are very similar to one another, but there's going to be a lot of things that we do later where being able to talk about and express things in terms of vectors ends up being quicker and easier and a little bit more elegant than expressing things in these giant square root formulas. So there is a reason for these things. There's a lot of similarity, but there's also value in our new understanding of it that we're getting through vectors. So I wanted now to do an example that's a little bit more complicated than the one that we just did, but ultimately very, very similar. So I think if you have a decent understanding of what we just did, this one should be pretty straightforward. So I would encourage you to pause the video, try this one on your own. If you're not sure, I'll sort of give a little bit of a hint here, and then go through it. So the problem gives us 2 points, a point A and a point B, and you're asked to find the value of K, which you notice is inside of one of the components. Find the value of K such that the magnitude of AB is 9. Right? So I think the hint that I would give you here is, can you figure out what AB is? And even if you can't find numbers for all of it, can you get an expression for what AB is? So in the previous slide, we reviewed that you can always find AB. You can always find any vector by doing the end point as a position vector minus the starting point as a position vector. So in our case here, we could say that OB is 9K4 minus OA, which is 5, 7, negative 3. And that means that the vector AB would be 4, K minus 7, and 7. So indeed, it's a little bit hard to say exactly what AB is, but what we now is we have an expression, so that the moment that somebody tells us what K is, we can plug it in and know what this thing is. Now in our case, we're supposed to find K, so now I'm going to use this. They tell me that the magnitude of this thing is supposed to be 9. Well, the magnitude of AB would just be 4 squared plus K minus 7 squared plus 7 squared. And I square root all of that. Right? I'm effectively told here that this magnitude should be 9. So now let's simplify this magnitude. This says that, actually this square root is sort of obnoxious. Let's just square both sides. So I can have 4 squared plus K minus 7 squared plus 7 squared equals 81. Now we'll move through and solve this. So I'm going to have 16 plus K squared minus 14K plus 49 plus another 49 equals 81. Now I'm gonna bring together some like terms here. I can bring together all of the constants and get 114 equals 81, and then I can subtract that 81 over. K squared minus 14K plus, let's see, that's going to be 19. I think that's 33. Last thing I need to do is figure out how to solve this for K. Fortunately, that's a quadratic, and we're really good at these. I'm just going to factor this. This factors into K minus 11 and K, oops, not plus, K minus 3. And that means that K could either be 11 or K could be 3. This problem was indeed a little bit more involved than the last one, but I want to point out to you that the majority of the sort of extra time in this problem came from me needing to solve a quadratic, right? Everything up here was sort of the same as the kind of problem that we dealt with in the previous one, right? We used this skill that we can find a vector. We used our new skill of the magnitude of a vector. We set it equal to something. Like I said, all the rest of this is us just solving a problem and using methods that we should be good at. Our next example is going to be fairly similar to this one, where you sort of start with one of these new skills, and then it's going to turn into you thinking about the problem through a lens that you've already understood before. So in this example, you're given 2 points, or rather, you're told about points A and B, which have position vectors A and B. And you're told then that C is the midpoint of AB, and they want you to find the exact distance from A to C. So I'd like you to sort of pause the video for a moment and think about what you think a good strategy for this problem would be. Right? I think my thinking here is if they don't want to know what C is, they're just asking for the distance from A to C. So my thought is, if I can find the magnitude of AB, if I can find out how far it is from A to B, how far will it be from A to C? Well, it'll be halfway there, right? So let's just find this and then cut it in half. So with that said, this should be a fairly simple problem. Pause the video, try it out on your own. So I'm thinking we're going to find AB by doing OB minus OA. You guys have heard me say before, I don't really like working with things in IJK notation. It's fine, but I'd prefer to just write these in their column vector forms. 2, 1, negative 2, minus OA, 5, negative 3, 3. So when I subtract these two things, I wind up with negative 3, 4, negative 5. And so if I now want to find the magnitude of AB, I just need to do the square root of negative 3 squared plus 4 squared plus negative 5 squared. That's the square root of 9 plus 16 plus 25, which is the square root of 50, which could be simplified further into 5 times the square root of 2. And I boxed that, but I suppose I shouldn't actually have boxed that, right? We weren't asked to find that distance. What they wanted is the distance from A to C, right? So the distance from A to C is going to be half of this. So, we could say the magnitude of AC is 5 root 2 over 2. Or we could write something like the distance AC is 5 root 2 over 2. So now that we've hopefully gotten down this concept of how to find the magnitude of a vector, or the distance between 2 points in three-dimensional space, I want to go in and sort of look at a few applications of how we can use this in problems that are a little bit more complicated. So in advanced vector problems involving distances, it's really common to leverage this concept of unit vectors. And we actually learned about them very, very briefly in one of our first lessons about vectors. But in case you forgot, I want to ask you to recall, a unit vector is basically just a vector whose magnitude is 1. Right? And it may be that in that lesson 3 lessons ago, I might have said that the length of the vector was 1, and now I have a fancier word. I can say that the magnitude is 1. I also want you to recall something else, and this is really important. Multiplying a vector by a scalar does not change the direction of the vector. It only changes the vector's magnitude. Okay? So for instance, if I had the vector A, and this was the vector A, and then I asked you, what is 5A, right? 5A is just that vector, but 5 times longer, right? So it's kind of this idea that we could take this vector here and just imagine that we have the same distance, the same length, but now it's 1, 2, 3, 4, 5 times as long. So similarly, let's say that I had a vector B that was like a really long vector, right? What would happen if I did something like 1/4 of B? Right? Wouldn't a quarter B just sort of be this idea that it's about a quarter of the length of this thing? Right? So scalar multiples can be used to sort of either scale a vector to be longer than it originally was, or to scale it down so that it's a little bit shorter. Now, before I go into this next slide, I sort of want to throw out one other idea. So imagine, if you will, that I had a vector A, and here it is, and I told you that the magnitude of A was 6, right? What would the magnitude of 1/6 A be? So if this vector right here has a magnitude of 6, and then I asked you to scale it down by a factor of 1/6, how long would that vector be? What would its magnitude be? Hopefully you can see really clearly, oh, this is really easy. That would just be 1, right? If this whole thing is 6 units long, and then you scaled the thing down to being only 1/6 that length, well, cool, that little length would be 1. We're going to use that in the next thing that we're going into. So I want to go through this sort of little example and then talk about how it connects to the thing that I just talked about. So first I want us to consider the vector A, which has components -2, 2, and -1. In part A, I'm going to ask us to find a unit vector that's in the same direction as that one. Right? So if I want to find a unit vector that's in the same direction as this one, I probably need to start by figuring out how long the vector currently is. I mean, maybe it's already a unit vector. Right? So let's start by figuring out what is the magnitude of A. Well, the magnitude of A will be the square root of negative 2 squared plus 2 squared plus negative 1 squared, which is the square root of 4 plus 1, which is the square root of 9, which is 3. Okay, cool. So this thing has a fairly reasonable magnitude. It's a nice, easy number. So if this vector is 3 units long, how could I get a unit vector that's in the same direction? Well, what I could do is I could just take that A vector and I could multiply it by 1/3. I could scale it down by a factor of 3. So that means I would just do 1/3 times negative 2 to negative 1. And so that would give me the vector negative 2/3, 2/3, and negative 1/3. All I'm really doing here is, as we've done with scalar multiples, just distributing this scalar factor into the 3 components. So this is my answer for part A. This is the unit vector that's in the same direction as A. Now, if I'm planning to use that later in the problem, I don't want to call this A because this isn't A. So I might do something like I might say let U equal that. I could imagine you could also do something like A sub U, because you're talking about like the unit vector version of A. Either of those things would be fine. I'm going to use the A sub U. I kind of like that. Now part B says now find a vector of magnitude 5 that's parallel to this original vector. Okay. Well, what I'm thinking is if I want it to be parallel to A, it just needs to be in the same direction as A. A unit vector is almost an expression of pure distance. This gives you a distance while keeping the magnitude 1. This is really easy to work with unit. Okay? So if they want a vector of magnitude 5 that's parallel to that, all I need to do is take that unit vector version of A I just found and scale it up by 5. Okay? So I'm just going to take the unit vector version, negative 2/3, 2/3, negative 1/3, and multiply by 5. Doing that's going to get me negative 10/3, 10/3, and negative 5/3. And there it is. This vector has a magnitude of 5, and it's in the same direction as this one. This problem is very, very similar to the last one. I just didn't break it into 2 steps. So I'd like you to pause the video and try this one on your own. You're being asked to find a vector of magnitude 3 that's parallel to 4i minus 3j plus 1k. So my first step in this problem is that I want to find the magnitude of that vector that was given. All right, so I'm going to start by saying that the magnitude of 4i minus 3j plus 1k, let's figure this out. This would be the square root of 4 squared plus negative 3 squared plus 1 squared. That's the square root of 16 plus 9 plus 1. That's the square root of 26. Okay, so the square root of 26 is not, maybe not my favorite magnitude. It's not nice and simple like the last one was, but it's not too bad. So now what I need to do is I need to turn this thing into a unit vector. So I'm going to take that vector, which you shouldn't be surprised I'm going to make a column vector because I like working with that better. I want to take this and I want to scale it down to being a unit vector. So I'm going to divide by the magnitude. I'm going to multiply by the reciprocal of the magnitude. Okay. Doing this is going to get me 4 over root 26, negative 3 over root 26, and 1 over root 26. So this thing is now a unit vector. Okay. Now they wanted it to be of magnitude 3, so now all I need to do is take that unit vector that I just found, negative 3 over root 26, and 1 over root 26, take that and scale it up now by 3. Doing that will get me 12 over root 26, negative 9 over root 26, and finally 3 over root 26. And there it is. It's not pretty at all, but I assure you this vector has a magnitude of 3, and it's in the same direction as this vector up here. Now I should point out we maybe could have saved a step here. We maybe could have skipped a step. And if you're barely holding on here, don't worry about skipping steps. If this has been really, really clear to you, you might have thought, or you might have noticed, couldn't I have done both of these operations right here? You can. You can use the denominator to scale down to 1 and at the same time multiply the top by 3, because you know that this will scale it down to being a unit vector and the numerator will sort of scale it back up to being the length that we want it to be. So if that's something that's really clear to you and it makes a lot of sense, know that that's allowable. But if it helps for you to just do this step by step and break it into a unit vector first and then go for scaling the magnitude up, know that you are welcome to do that. As we move into our last example, I want to do two things. One, I want to let you practice vectors more, but two, I want to remind you of something. As we proceed deeper into our study of vectors, and actually not just vectors, but all of math, it's really, really important that you not fear variables. It's going to be really common that we'll need to work with not just numbers, but also expressions that have variables in them. And I want to remind you that variables and problems we really just treat like numbers. And so it means that we're going to get expressions and those things are going to be a little bit complicated, but that's okay. We're using skills that we already know how to work with. So I want you to sort of keep that in mind as we go into this problem. So in this problem, the point A is given by 2, -1, 0, and the point B is such that OB, and remember what OB is. OB is a position vector. So the position of point B is given by this thing, which seems to depend on T. So it's almost like B is maybe moving, like B is sort of in different places depending on what T is. And this problem is now saying find the possible values of T such that the magnitude of AB is 10. So I want to point out to you, this problem is actually really not any different than anything else we've done. The only difference is that I'm throwing a variable in here. Right, so if you feel like you've got a good idea of how to do this, I want you to give it a shot on your own. If you need some guidance, I'll go ahead and get you started. So we're told that the magnitude of AB is supposed to be 10. So let's do what we've done before. Let's start out by figuring out what AB is. How am I going to get AB? Well, AB is going to be OB minus OA. Okay? And so maybe you're concerned about OB is, you're like, OB is this like weird thing over here. If that's weird to you, express it as one vector. I mean, they said it's a vector, so write it as a vector. This thing is basically 2 minus t for its x component. It's 1 plus 3t for its y component, and it's 1 plus 2t for its z component, right? So when I'm asking you to find vector AB down here, I'm just saying make it 2 minus t, 1 plus 3t, and 1 plus 2t. Take that and subtract OA from it. So 2, -1, 0. So you should very much be able to do that. And you know, if you haven't tried this on your own at this point, try picking the problem up from here. Try writing an expression for AB, finding its magnitude, and setting that equal to 10. So as I keep doing this, 2t minus, so let's see here, 2 minus t minus 2, those 2's are going to cancel out and just leave me with -t. In the middle here, 1 plus 3t minus -1, that's going to wind up being 2 plus 3t. And this last thing, 1 plus 2t minus 0, oh, I mean, that's really easy, 1 plus 2t. So that's AB, right? Next thing, I want to find the magnitude of AB. The magnitude of AB will be the square root of -t squared plus 2 plus 3t squared plus 1 plus 2t squared. Now, some of you may already sort of be getting scared of this thing, right? Oops, I just realized I dropped a parentheses there. You may already be scared. You're like, oh my gosh, there's so much going on here. We can do this. I want you to remember that you've gotten this far, so we're going to push through this. We're going to break this down into small pieces and just keep going. So, simplifying the inside of this is going to get me t squared. Now this part right here, I'm going to need to multiply out. I'm going to write this in red. Please don't just try and distribute this power in. You can't do that. You really need to see this as 2 plus 3t times 2 plus 3t. We're foiling this out. We're binomial multiplying this. In here, we're going to get 4, that's from 2 times 2, plus 12t, that'll be from 2 times 3t and 3t times 2, plus 9t squared, that's the 3t times the 3t, And then plus, we'll do a really similar thing over here. 1 plus 4t plus 4t squared. This magnitude is supposed to be equal to 10. Now, I'll admit, this thing on the left is sort of scary looking. So let's do two things at the same time. One, I don't like the square root, so let's square both sides, right? This would be a 100. So 100 is, and at the same time, let's pull together the like terms. T squared, 9t squared, and 4t squared, that's 14t squared. Got those. Next, let's get the t terms. I've got 12t and 4t. That's 16t. And finally, let's get the constant terms, 4 and 1. That's plus 5. Okay? So now I've just got a quadratic that's equal to 100. We know how to solve quadratics. The worst case scenario is that this is going to be the quadratic formula. And even then, I have some good news for you, right? So let's move everything over to one side. 14t squared plus 16t minus 95 equals 0. This might be factorable, but I doubt it. And even if it is, I don't want to try. Let's do quadratic formula for this. T will be negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay? And the good news is, as far as IB is concerned, this is fine. Any answer that you have that's algebraically equivalent is acceptable. Okay? For those of you that might have already computed this, I'm going to go ahead and punch into the calculator and figure out what those values are just so that you can check them. The two values I got from the calculator were negative 3.24 and 2.095, so 2.10. So if you use the calculator, those are what you would get. There was nothing in the context of the problem that told us that a negative t value wouldn't have been acceptable here. So these are both correct answers. So I know that this was sort of a long problem, but what I wanted to show you is that these are all steps that you're capable of doing. We just need to sort of persevere in problem solving and get through it. So I really hope all that made sense. If you have questions, please, of course, reach out to me. And I wish you the best of luck as you work through the assignment.